I guess everyone is making their way from the rooms back to the main meeting. Welcome to night 2 of Washington Conservation Guild's 3-ring circus. Be prepared to immerse yourself into a world of high-tech and analysis, because tonight's theme is technical imaging and scientific research. I'm Joanna Baker, a director at the WCG, and we will begin tonight's talks with a few words from Jane Holt, the WC president, if she has anything she wants to say.
Jane is running a little bit late, so I'll just make a few announcements. I'm Rachel Greenberg, the vice president, Washington Conservation Guild. So just want to thank everyone for joining the second ring of our virtual 3-ring talks this year. I know everyone is hoping to be back in person, but at least this way we have a lot of people from much further abroad, much further than the local Washington region. And this way everyone gets to, or has a chance to attend all 9 talks. So just a reminder that we do have the 3rd ring taking place next Thursday, January 13th. Our sponsors were also really looking forward to seeing everyone back in person. So I just wanted to thank them as well. That's AIC, Gaylord Archival, Hyrox, Hollinger Metal Edge, Small Core, Talus, TrueView, and University Products. And for other things coming up for WCG, we have, besides the next part of the 3-ring, we have our February meeting, February 3rd, that is on preserving Indigenous culture through 3D technologies. And we also have a webinar coming up. It'll be free for members, and this is on federal contracting. It'll cover some of the nuances and language that's used in federal government contracts. That will take place on Thursday, February 24th at 5 p.m. and registration information will be sent out very soon for that. So with that, I will hand it back to Joanna.
Thank you, Rachel. Just a few reminders. Tonight's talks are being recorded, as you saw on your screen. And please put any questions or comments you might have in the chat. Your speakers would love to answer. We're going to have a couple minutes after each talk for questions, but we'll also have some time at the end. So if you do think of something after that time period, happy to give your questions. So our first speaker tonight is Wendy Rose. Wendy Rose is a freelance wall painting conservator with expertise in digital documentation techniques. She is currently a contracted associate paintings conservator at the Smithsonian American Art Museum, conserving The Uprising of the Mujeres by Judy Baca, and a consultant at the Getty Conservation Institute, where she is researching the application of photogrammetry. I'm going to totally photogrammetry. I am sorry. To the I practiced it, and then I said it wrong. To the conservation of wall paintings. Wendy completed her MA in the conservation of wall painting at the Curtin Institute of Art in 2019. And a fun fact about Wendy is that she grew up in Hawaii, in Maui, and she is very much so currently struggling with the recent DC cold snap. Take it away, Wendy.
Great, thank you, Joanna. Just gonna share my screen here. Okay, it's not really letting me share my second screen. That's a little weird. Okay, let's see. Okay. Good evening, everyone. Can you see just the main slide, the intro slide? Just checking to make sure it's working. Okay, I'm just going to assume it's working. My name is Wendy Rose, and I'm a wall painting conservator and contractor at the Smithsonian American Art Museum. Tonight, I'll be presenting my work at the Lunder Conservation Center, documenting the portable mural entitled The Uprising of the Mujeres, using multispectral photogrammetry and highlighting the ways that photogrammetry, a 3D imaging technique increasingly used in wall painting conservation, can support painting conservation in a museum setting. The Uprising of the Mujeres is a portable mural by artist Judy F. Baca, and it was acquired by the Smithsonian American Art Museum in 2019. Baca is a leading interdisciplinary Chicana feminist artist born in Los Angeles and currently based there as well. The Uprising of the Mujeres was painted in 1979. Baca completed the mural immediately following her return from a mural training workshop founded by Mexican muralist David Siqueiros in Mexico. According to Baca, during the workshop, the other attendees, the all male artists, had proposed a mural design for the workshop that was meant to criticize women as the primary conduits of consumerism and, by extension, capitalism. The central figure in the design had a woman with a funnel down her throat, taking in all sorts of goods and consumables. So as a response to that rather sexist design, she proposed a mural similar to the one that you see in front of you on the screen, but it was rejected by the other attendees of the workshop as the design to finish the workshop with. So when she returned to Los Angeles following the workshop, she painted this mural herself. The Uprising of the Mujeres depicts a powerful indigenous woman on the far right, leading female and male workers in an uprising against exploitation. The mural is 24 feet by 8 feet, and it's comprised of 6 painted panels, each measuring 4 feet by 8 feet. The painting is an acrylic emulsion on masonite board with lumber supports shown here, and then backed by another 4 foot by 8 foot masonite board to protect the interior, followed by cleats that allow the panels to be hung. I was brought on with the support of the Latino Initiatives Pool to conserve the panels prior to their installation in the redesigned galleries. One of the aims of the panel's conservation and my time at the American Art Museum was to undertake outreach and to promote the murals to the public, and so that they are better understood and appreciated. However, good quality images are critical to help audiences engage with the work, but this can be particularly challenging with large scale murals like this one, as many of the interesting details of the murals, like here on the coin written "In Him We Trust" rather cheekily, and the incredible detail in the dollar bills, those are lost when you're looking at a very large overview of the mural. You're sort of overwhelmed and you can't appreciate the details. And it is difficult to get high resolution images of these details within a large picture of the mural. Additionally, we wanted to have high quality documentation for conservation issues, like shown on the lower image here. The nails and screws that were used to connect the painted masonite board to the lumber supports are starting to pop out and emerge from the masonite. And we want to be sure that we can understand if this is ongoing, if they're stationary, if this happened when the painting was made. So high quality documentation is quite important. However, when we attempted to image the panel in a single image, as shown on the left here, the single image was too low resolution to see the conditions particularly well. This is a detail of that single image. You can see these are actually the nails that have popped through the paint layer, but you can't really see any details or determine that they're nails from this image. So you can't tell if they're worsening or anything over time from these images. Additionally, the panel required a lot of handling to get it on the easel safely. It took 4 of us working together to safely get the 4 foot by 8 foot panel onto the easel, which certainly creates some risk for ourselves and for the painting. And the image itself is not perfectly rectified. So the single image is going to contain the distortions of the camera and of the lens, particularly as it is set far away from the panel. And if we did not place the panel perfectly vertical, it would also have distortions in that way. So one option to address the low resolution would be to make a stitched image of the panel. So many overlapping images stitched together. However, this method inevitably results in distorted edges between the connecting images and an inaccurate final image. So I decided to implement an imaging solution that is commonly used in wall painting conservation called photogrammetry. Photogrammetry is a technique that uses overlapping images to generate 3D digital models. While this 3D imaging technique can be used to make 3D models like this one you see here, it has advantages for painted surfaces as well. The 3D model can be used to produce an orthophoto, which is a rectified image of the subject, or an image where perspective or distortion has been removed. As you can see in this example on the left, I'm showing the panel with perspective distortion, and then it's corrected when it becomes a rectified image. The orthophoto is not a stitched image, but a mosaic, as you can see on the right, where the photographs are projected back onto the 3D model of the surface for maximum accuracy and minimum distortion. With this technique, the final image is an amalgamation of all of the high resolution images taken, and there's no distortion to the image. So you can imagine why this is useful in wall painting conservation, because it allows us to have an undistorted image of a large painted surface that is often impossible to capture in this way otherwise. Frequently, you can't move further away from the wall painting if it's in an enclosed space, problems like that. So the orthophoto gives us a high resolution, undistorted image, and I wanted to capture in visible, UV, and infrared. The UV image and the infrared in particular, we could see the high level of detail in these bandwidths of light and learn more about the condition and the history of the piece. The orthophoto can act as a base map for graphic documentation, and it would result in each panel being highly documented in high resolution completely. So every inch of the painting would be very thoroughly documented, and it would help us reduce panel handling because we could just move the panel, lean it against the wall, and even though it's at an angle to the camera, the process can then result in a rectified image. The photogrammetry would also create a digital elevation model, which is an image where each pixel represents the relative height of that point on the surface. And we could use this to measure and monitor the screws and nails in the panels. And finally, we can create a 3D model where we can examine it and take measurements on it. It's similar to the one I showed you in the previous slide of the stone. And that can also help us with our outreach goals. So each panel was captured in visible light using LED panels, UV induced luminescence, and infrared reflected light. The camera was 1 meter away from the panels, resulting in a resolution of capture of 1/10 of a millimeter per pixel. That means that each pixel in the resulting image was equivalent to 1/10 of a millimeter on the painting. So this created what we wanted, the highly detailed ortho photos, but it also required significant capture and processing time. On the right, you can see I have to use a flashlight to focus the camera before each capture in UV light, which was kind of tedious, but I had fun. Okay, so the resulting ortho photos had a much better resolution than the single image. On the left, this is the same detail I showed you before from the single image, and on the right is that detail in the ortho photo. So now in the image, we can see the nails and the loss of paint due to the nails pushing through. We can also see brush strokes, crackler, and we have just a much, much better record of the painting. The UV imaging also allowed us to see a lot of details in the coating. If we tried to take these images from much further away, we wouldn't have been able to see almost any of the luminescence, or getting close, we could only pick a couple areas, but doing the UV photogrammetry, we could see the entire panel and all of its conditions. And here you can see some heavy coating that had been applied. And on the right, we can see areas of retouching, particularly over where nails have pushed the painting off and the artist actually went in and retouched those areas. So that gives us a sense of how long ago the nails have been an issue. and we can keep an eye on them going forward. Under infrared light, the orthophotos were able to show us some great details of the underdrawings that wouldn't have been visible in a single image. On the left, only one of the panels showed this preparatory technique, which is called pouncing. It's a mural painting preparatory technique that goes back all the way to at least the Renaissance, where the design would have been drawn by the master, holes poked through to the design, and then the design laid on top of the wall painting and charcoal dusted over the top to essentially transfer the design to the wall. So Baca uses this historic mural prep technique only on one panel to outline mostly the figure of this woman, as well as other just line drawing techniques that the photogrammetry was able to show. And on the right, we can see more line drawing preparatory drawings for this figure on the far left. So the results I'm showing you here is the collected ortho photos of each panel all lined up to recreate the mural. This is in visible light, the infrared reflected, showing the underdrawing and preparatory work. We also saw lots of charcoal sketching to kind of create underlying shading for the painting. And the UV-induced luminescence. Here, again, we can see areas of retouching. The coating was applied differently on every panel and presents differently. I can see areas of drips in an incredible amount of detail. And when we produce the digital elevation models, so on the left here, this is the digital elevation model of this panel here. This is a heat map showing the relative heights of these areas on the masonite. So these are very small differences, less than a centimeter, but you can see that the masonite is bowing and distorted in different ways. So this will let us have a better information about the distortion of the masonite panel. And on the right is a different way to visualize the digital elevation model. This is the model of this section of painting up top. And we can see in the topography view, here is the screw or the nail pushing through. Here's the nail here. And on this model, we can actually take height measurements. So like down to quite a small, down to essentially the resolution size. So down to 1/10 of a millimeter. And this way we can actually measure and track whether or not the nails continue to push out of the board. I also found that having the 3D models, this wasn't part of my plan, but it supported remote work in the time of COVID, and particularly the snowstorms when we weren't able to go into the museum, because I could examine the panels at very high resolution and also take measurements on them. So when completing condition reports, if I wanted to know what the measurement of a certain condition was, I could just open the 3D model and make that measurement. And then these 3D models will also support our future outreach so that we can promote this incredible mural to the public. So just to summarize, the photogrammetry was able to provide high resolution, undistorted, visible IR and UV images of each panel. We can monitor distortions in the masonite and changes in the nails and screws. We can make measurements on the panel with the 3D models. We can share the mural in incredible detail more widely. And while the large scale of the mural instigated the use of photogrammetry, all these benefits are the same regardless of the size or the planarity of the object. So this could be applied to a small painting or an object or anything really, and you can get this three-dimensional information. So thank you for your time and attention, and many thanks to the Latino Initiatives Pool and my amazing colleagues at the Lunder Conservation Center. My contact information is at the bottom if you have any questions.
Oh, thank you, Wendy. That was fascinating. The question, how long did this take you, this project?
So at the beginning, one panel took me maybe like 5 or 6 days to do all of the light sources and all of the image overlap. I was also taking of the back of the panels. So total, all 6 panels took me maybe like 6 or 7 weeks of work.
Wow.
So it was a lot, but I have gotten
So detailed.
I've gotten a ton of usage out of the images, and the level of detail was my decision. You can always back off and reduce the number of images for your purposes.
Yeah, but it seems like it's priceless for a record of the mural. Yeah, and if anyone has any questions, let me know. And even we're probably going to move on to the next talk, but we'll circle back if you have any questions for Wendy. Great. Thank you, Wendy.
Thank you.
Our next speaker is Joan Walker. She is a conservation scientist at the National Gallery of Art, where she was hired in 2016 as part of a Mellon Foundation sponsored research initiative investigating historic photographic processes. She holds a PhD in inorganic chemistry from Indiana University. Her work at the National Gallery includes the analysis of photographs and other works of art, and she is currently researching non-invasive spectroscopic methods for interrogating artist materials and layered structures. Prior to joining the National Gallery, Joan held positions at the Indianapolis Museum of Art and Indiana Historical Society, where in addition to her duties as a conservation technician, she also served as a hand model for a book about genealogical research. We'll have to ask about that later. Welcome, Joan.
Thank you so much. Great. Okay. So tonight I'm going to be telling you about some of my work. I'm looking in using Reflectance FTIR Spectroscopy for understanding layered structures, particularly photographs. And so this, some of this work appeared in part in a presentation given to the Microscopy and Microanalysis meeting in 2021. So FTIR spectroscopy is well established as a characterization tool, is a very important characterization tool in cultural heritage research. And so I'm just showing here some examples of different types of instrument configurations that might be found in a museum laboratory. And that includes benchtop systems and microscope-based systems that might work in transmission or use various accessories like attenuated total reflectance or ATR crystals. So for cultural heritage purposes, probably the most important column here in this table is the one at the far right. And that gives us an indication of how invasive this spectroscopic technique might be for our sample under analysis. So does it require us to take a sample from a work of art? Does it require contact with that sample in order to acquire spectra? And that is particularly important for photographic materials because very rarely are we able to take a sample from a photographic work of art. So to use FTIR spectroscopy in the analysis of photographs, two modalities are most commonly used, and those are attenuated total reflectance or ATR, as well as external reflectance. And so I'm just showing here a couple of different instrument configurations, although others are possible. So on the left, I've got a FTIR microscope that has been fitted with an ATR crystal to collect spectra from your sample. And on the right, I've got a external reflectance spectrometer. This is a compact portable system that's been mounted onto a tripod, so you can take it wherever you want and collect spectra that way. But you can also do reflectance measurements using a microscope or vice versa. So other configurations are possible. But for the in situ measurement of FTIR spectra on a photograph, what's really important is how does your infrared radiation interact with your sample? And so as I mentioned, ATR requires contact. And so here I'm showing the ATR objective. So the crystal is actually just right at the tip of this objective and it is in contact with the surface of a photograph. And so your infrared radiation is directed down through that objective and through the crystal and then only penetrates to a very shallow depth into your sample. So depending on the materials used, usually it's on the order of around a micron. And so because of that, ATR is a very surface specific technique, and that can be quite useful. Reflectance FTIR spectroscopy however, is a non-contact technique. And so we actually do have an air path in between your sample and your spectrometer. And so we're literally just bouncing infrared radiation off the surface of the object. And so because of that, the infrared radiation that's collected by your spectrometer might include components both from the specularly reflected light as well as diffusely reflected light. And that comes from deeper down in your sample, depending on your instrument configuration and other factors involved. And so because of the complexity of the signal that's received by your spectrometer, the spectra collected in reflectance mode can be somewhat more difficult or complicated to interpret. And so what I wanted to do was just systematically look at some very simple sample systems to try to understand how these various factors influence one another and influence your spectra that are collected. And therefore, what kind of information can we actually extract from reflectance spectra in order to understand samples better? So I'm going to start by showing just some examples from some of the study collection at the National Gallery. So here are some sample photographs from the historic photo process set that was made available by the Photographic Materials Group. And that contains examples of all of the major paper-based photographic processes of the 19th and early 20th centuries. So we'll just go through those kind of one by one. So a cyanotype or blueprint is comprised of Prussian blue image material that's embedded in the surface of a cellulose or paper support. And so this is considered a single layer photograph. What that means is if you look at it in a cross section, you don't see any layer differentiation. And so this is the backscattered electron SEM image, and we just see paper that is the support of the photograph. So the image particles in this example are too small to be seen by this technique. And so the Prussian blue image is actually just embedded in the uppermost cellulose fibers of the paper surface. So the reflectance FTIR spectra that we collect from this photograph are actually pretty straightforward to interpret. So if we look at an area of low image density, so a white area that contains very little image, we just see signal that's attributable to the cellulose paper support. And that compares to a reference paper spectrum shown in gray at the bottom. But if we look at a really dark area of the max area of image density, where we have a lot of the Prussian blue image material, then we can clearly pick out the characteristic C triple bond and cyano stretch from the Prussian blue image material. Salted paper prints are also single layer photographs, but here the image material are metallic silver nanoparticles. And so silver particles don't have a characteristic vibration in the mid-infrared. And so essentially wherever we look at collect spectra from this salted paper print, we're just going to see cellulose because that signal is not influenced by the presence of the silver particle. So we just see cellulose. Now, if the silver image is contained within a binder layer, then FTIR spectroscopy typically allows us to identify that binder material, and that's important for process identification. And so here I'm showing an albumin print, and that consists of silver particles that are held within a protein, albumin, egg white protein binder layer that's supported by paper underneath. So if we collect reflectance FTIR spectra, we can clearly identify the amide-1 and amide-2 bands from the protein. And what's interesting about these spectra is that we actually see no contribution to the reflectance spectrum from the underlying cellulose support, even though the albumin layer is thin. It's only about 20 microns or less thin. But we're just, the specularly reflected light is dominated by the shiny surface of the albumin protein. So we're just seeing that specular signal from the protein. However, if the photograph contains a highly reflective layer underneath the binder layer, then it is possible to see spectral information from it. And so here I'm showing a silver gelatin printed out print. And so it is comprised of a paper support that has been coated with a bright white baryta layer, and that contains barium sulfate. And then the silver image is held within a binder layer that is comprised of gelatin protein. And so we can clearly see the protein signal in the Reflectance FTIR spectra. What's interesting is that even though this protein layer is on the order of 50 microns thick, we can actually see signal that's attributable to the underlying sulfate bands from this barium sulfate containing layer. So because it's so highly reflective, we can actually see infrared signal from the baryta layer as well. But what's also interesting is that if we compare the spectra collected in an area of low image density versus an area of high image density, that signal that's coming from the sulfate layer seems to be further modulated by the presence of the silver image particle, almost as if they're acting as a filter. And so we're modulating the intensity and apparent phase of those sulfate-related bands. So here is a silver gelatin developed out print, which is very similar in structure to the printed out print that I just showed you. It consists of a silver image that is contained within a gelatin binder layer on top of a baryta layer that's supported by paper. Now, this particular example is a matte surface photograph, and to make the surface matte, the photograph has silica particles that are embedded in the binder layer. So we can actually see that if we look at the spectrum collected in a white area, we can see the protein, the gelatin protein of the binder layer. We can also see the silica band, which is a very broad band at around 1100 wave numbers. And that overlaps the sulfate bands from the baryta layer. So there are multiple overlapping bands in that region. However, if we look in a Dmax maximum density area, we see that the silver image actually completely blocks the underlying sulfate bands from coming through. So we only see silica in addition to the protein. And so what I'm hoping that this series of examples is showing you is that these reflectance FTIR spectra actually contain a great deal of information about the structure of these photographs, and even can give you information about the mid-infrared silent silver particles. So to further kind of look at this, I will like to point out that the ATR spectra are not influenced by the silver image density. And so for these same reference photographs, collecting spectra using an ATR crystal, we clearly identify the binder layer, whether it be cellulose or protein, as well as that silica from the matting agent in the developed out print. But we don't see a big difference between spectra collected in maximum versus minimum image density areas. So the silver is not influencing the spectra collected in this way. So we're getting different types of information using these two different spectroscopic techniques. And so it gives us different information, even though we're interrogating the same samples. So to further kind of try to understand how these different layered materials interact with one another and how that can influence the reflectance FTIR spectrum that we collect, I'm going to show some examples from the photograph conservation study collection. And so here are a few different types of photographs, different photographic processes that have been coated with various types of materials just for study purposes. So starting with the example of a beeswax coated salted paper print, which if you remember a salted paper print, the original surface is just a cellulose paper surface. We can clearly pick out those cellulose bands in the spectrum collected using an ATR crystal. And then in the beeswax can be identified by very sharp bands, aliphatic CH bands, as well as the wax ester C double bond O band. And so in the spectrum acquired in the coated area of this print, those bands appear in addition to bands from the cellulose, which we can still pick out, collected in ATR. Now in reflectance FTIR, however, we see very little to no contribution from the underlying cellulose in the coated region of the spectrum. So even though the cellulose has an identifiable spectrum, in the uncoded regions of that photograph, sample photograph. In the coded regions, we clearly see the beeswax, but the spectrum is completely dominated by that beeswax signal because the cellulose surface is not very reflective. So to show, again, the influence of the substrate reflectivity in the reflected spectrum for these coded photographs, I'm also going to show the example of an albumin print. And so we can clearly, again, pick out the protein bands from the albumin protein in the uncoded section of the photograph. And then those protein bands are hardly changed at all in comparing the spectrum collected in the coded region, which is shown in the blue trace here. So we can pick out the beeswax from those CH bands, as well as the wax ester that appears as a small shoulder on the amide band. But because the albumin is itself somewhat glossy, we can see in reflectance contributions from the protein as well as the beeswax coating that's over top of it. Now, of course, beeswax and albumin and protein are all very different chemical compositions. So I also want to show the example of two collodion prints. So collodion is prints have a binder layer that's composed of cellulose nitrate. And so these two examples only differ in their surface sheen, and that can be modified during processing to make it either glossy or matte, essentially through burnishing. And so in the reflectance spectra collected in the uncoated portions of both of these photographs, we can identify the chemical identity of the binder layer, the nitrate, and the modified cellulose, the cellulose nitrate collodion. But then when we look at the beeswax coated section of these sample prints, we see that the spectra look really different. And so we can clearly pick out beeswax once again, but the signal that's coming from the underlying collodion surface is greatly modified between the two. So there's no chemical difference here because we just have beeswax that's on cellulose nitrate. However, the way that these layers are interacting, the reflectance of these layers are interacting is changing the reflectance signal that we're picking up. So reflectance FTIR is a really powerful tool to interrogate samples completely non-invasively. Now, because of that, the interpretation of spectra can be challenging, but we're gaining a better and better understanding of the complex factors involved. So the physical and optical attributes of layers contribute to the information that is gained in reflectance spectra. And even for relatively simple sample systems, like the ones I've shown this evening, a major lesson, I think, is how even small changes in things like surface texture can drastically affect the spectra that you see. So, but as we better kind of learn how the physical, chemical, and optical properties affect reflectance in the infrared region, I think we will be better able to exploit these spectra to use the technique to identify materials and also probe other questions like condition and surface properties and layered structure in photographs, as well as many other types of cultural heritage samples. So I would just like to acknowledge my colleagues in the Scientific Research Department and Photograph Conservation Departments at the National Gallery. I'd like to thank the organizers of the meeting, and I also include my contact information. So please reach out with any questions, or if you have other Reflectance FTIR stories you'd like to share with me, I appreciate that. So I'd also take any questions now.
Thanks so much, Joan. That was a really fantastic talk and such useful research. And I learned so much about photos. Great. Well, thank you so much. We are going to, sorry, I didn't start my video. We'll move on to our, let me see if I have any questions here. There were some questions from the first talk, and I think they've been answered by Wendy. Oh, here we go. This is great and very helpful. Is your reference library for your reflectance measurements on the study pieces shared or public access in any way?
So we have not published this data yet. I think yeah, sharing this in repositories for reflectance. I think a lot of people are talking about that right now. I know the infrared and Raman users group is interested in starting to collect reflectance FTIR data to include in some of their databases. And I know of a couple of other libraries that have been kind of put in data repositories. And so I think that's a great idea. We have not, I have not contributed to any yet, but I think that's something that, yeah, I think a lot of people are really interested in making sure that more and more people have access to these spectra so we can all work on them together.
Great. Okay, thank you, Joan, and we'll let you know if we have any more questions. Our next speaker is Kristen Watts. She is currently a National Research Council postdoctoral fellow working in the Materials Measurement Laboratory at the National Institute for Standards and Technology, or NIST. She obtained her MS in chemistry from Villanova University in 2015 and a PhD in chemistry from the University of Arizona in 2020, where she specialized in applying infrared and Raman spectroscopies to monitor the formation of degradation products in organic materials. And her fun fact is that she she does dance and circus arts in her free time, and her current loves are blues dancing and lyra. Great. Okay, welcome, Kristen.
Thank you so much for that introduction, Joanna. Let me just go ahead and share my screen. All right, so good evening or good morning to those of you who are joining us from the other side of the world. I'm so glad to be here. Thank you again, Joanna, for that introduction. So I'm really excited to have this opportunity to talk to you all today about the work that I've been doing during the course of my postdoctoral fellowship here at NIST. So let's just jump right into it. So I know I probably don't need to belabor the point to this fabulous audience about red lakes. Red lakes being ubiquitous throughout all types of cultural heritage, found in paintings such as this one shown here, which I just pulled from Pigments Through the Ages website, which has a double layer of a Kermes lake and a Madder lake, so two red lakes sitting on top of each other. They're also found in illuminated manuscripts and the like. And yet, even though they are so ubiquitously used throughout cultural heritage, they are notoriously hard to identify, particularly in a non-invasive manner. So pre-2000s, identification of organic red pigments like red lakes were primarily done by high-performance liquid chromatography, or HPLC, which was great in general, isolating these compounds from more inorganic types of pigments. But ultimately, this type of analysis for identification purposes is not really feasible going, is not ideal in the sense that it's completely destructive to the sample, and that in the extraction procedure to remove these red lake pigments from the material, there are frequently often quite harsh and complex extraction procedures that must be employed, using oftentimes very corrosive chemicals like hydrofluoric acid. And so around 2006, the Casadeo and Van Dyne group published this work, which I'm citing right here, in which they applied surface-enhanced Raman spectroscopy to identify red lakes in cultural heritage objects, which was actually a really great finding, because Raman spectroscopy in general really does a great job of granting chemical specificity for identification, and also has the possibility of non-invasive measurement. And to kind of piggyback based on the last talk, is complementary to the sorts of data that one would get using an infrared spectrum. The problem historically, and why it hadn't been used until 2006 very frequently for the identification of red lakes, is that red lakes are often really quite poor Raman scatterers. They don't scatter light in Raman scattered light very efficiently. And then also piggybacked on top of that, there is frequently a very large fluorescent background. So the great thing about surface-enhanced Raman spectroscopy is that you get a 5 to 7 orders of magnitude increase in your Raman signal, so that you can actually start to see the specific bands to your material of interest above the fluorescent background. So this figure I've just pulled from the Van Dyne and Casadeo's group paper that again I'm citing here, in which a normal Raman spectrum of carminic acid, you just have this broad kind of featureless spectrum, whereas when you apply the SSE-RM methodology, you now can see characteristic bands for carminic acid start to appear above that fluorescent background. Another type of approach of Raman spectroscopy that then also started being applied for the analysis of red lakes is Fourier transform Raman spectroscopy. Now, these two techniques are great, and they really started scientists thinking and rethinking about possibly using Raman spectroscopy as a less invasive approach to identifying red lake pigments in cultural heritage objects. The problem with these two techniques, on the one hand, SSE-RS, you still are going to be invasive to your sample, and that you need to apply some sort of nano-patterned silver substrate onto your sample in order to even induce the SSE-RS effect in the first place. And then with Fourier transform Raman spectroscopy, the instrumentation involved is often quite large and bulky, requiring liquid nitrogen cooled detectors and complex instrumentation. And so it's not really feasible for portability or analysis of objects in situ. And so the goal of my research was to try to develop a non-invasive type of Raman spectroscopy of organic red lakes, which maximizes the Raman signal while minimizing the background fluorescence, and then ultimately with whatever I develop, having the possibility for in situ and portable measurements. And so in that regard, I started looking through the literature and found that there is a recent movement in the Raman spectroscopy field towards more data processing focused methods. And what all of these methods have at their core is one really interesting aspect of light theory, which I'm going to summarize quite briefly here. So in a Raman spectroscopy experiment, we have a laser at a fixed excitation hitting our sample, and then we are collecting the Raman scattered, the inelastically scattered light, and detecting that light, and that generates our Raman spectrum. And so if we change our excitation wavelength, we are necessarily changing the wavelength of the Raman scattered light, because it's going to be scattered to a different degree, because by changing the excitation wavelength, we're changing the energy of the light. But what's interesting though, is even though the Raman scattered light does change in wavelength, any fluorescent or any sort of emitted light from the sample does not change as a function of a change in the excitation wavelength. And this is a process known as Koch's rule. The only thing that will change if you change the excitation wavelength for fluorescence is just the intensity of the fluorescence, not the position of the fluorescence. And then furthermore, as an added benefit, thinking about, other types of stray light we might have in our measurement, room light that might get into our camera, or fixed pattern detector noise, things like that, those are completely independent of the excitation wavelength. So just doing something like stepping our excitation wavelength, we should only see changes in our Raman signal and no changes in any other aspect of the collected data from the experiment. So there's a whole host of techniques that are predicated on this premise, but the one I'm going to be focusing on, and the one I've based my data processing style of Raman on, is the sequentially shifted excitation Raman spectroscopy experiment. And so what I can do is I can take my laser that I'm using, and then specifically in this case, I'm going to be using a diode laser, because you can fine tune the step size of the wavelength, of which wavelength you're using, by actually applying different temperatures to the laser itself. So in this example, in the blue here is the Raman spectrum that I generated from an incident wavelength of 785.08 nanometers, or an 18 degrees Celsius laser. And then by incrementally stepping through 4 degrees Celsius per step, which corresponds to about 0.24 nanometers or 3.6 wave numbers per step, I can slowly shift my obtained Raman spectrum. And I should point out that this x-axis, the Raman shift, is calibrated towards this first excitation wavelength. The only thing that changes is the Raman signal, and the fluorescent signal does not change, that it's sitting on top of. It doesn't change in spectral space. And so through a series of relatively straightforward processing algorithms, you can actually extract out the Raman signal completely free from any sort of fluorescent background. So the reason I chose Cinnabar is while it does have some slight fluorescence, we do have these strong Raman bands that you can see quite clearly. And as you can see, any of this fluorescent background that these bands are sitting on top of has now been completely isolated, and only the Raman modes are remaining. Now, I'm happy to talk about this algorithm more in depth. I don't have time for this talk today, but if you are at all curious about the algorithms that are really quite straightforward to code in something like MATLAB, this paper right here is really a great resource for that. So credit where credit is due. I'm not the first person to think about applying this technique to cultural heritage. In fact, there is a commercially available portable version of a point spectroscopy instrument that was used first by Conti et al. And this work, the work that they did was mostly towards studying inorganic pigments on terracotta sculptures, but they did do a first preliminary analysis of a madder lake powder, where they showed that the sequentially shifted excitation Raman point spectrum is incredibly comparable to the same spectrum of the same sample from the Fourier transform instrument. And that if the same sample was measured by a fiber optic dispersive Raman probe, the signal is completely swamped by background fluorescence. And even when it's background corrected, the spectrum is no longer faithful to what the true spectrum is actually of the madder lake. The rest of these three works that I'm citing here all applied this point spectroscopy technique to the study of synthetic organic pigments, with the exception of Paz et al., who also noted the presence of indigo and purple codices. And so with my work, the reason my work is unique is that I'm going to be incorporating it, first of all, into a microscope to engage in Raman hyperspectral imaging on a very small scale, so we can have a nice spatial resolution for imaging an object in situ and being able to discern where pigment particles are relative to each other. And I'm also going to be monitoring natural organic red lake pigments, specifically focusing on Carmine Lake and Lac Lake, and also a slightly modified processing algorithm. So a quick walkthrough of my instrumental setup. This is the laser that I'm using. It's a 785 nanometer laser housed in this laser diode and temperature controller, so I can directly program in the current I want my laser to operate at and the temperature. The working setup is in a light uncontrolled area and a light controlled area. So in the light controlled area is basically a dark box in which I've situated my Raman microscope. So this is where the analysis actually occurs. And everything outside of this dark box is in a fiber optic. So there's no risk of exposure to a free beam at any point. Quick walkthrough of what the microscope actually looks like. So we have this laser. This is a 785 nanometer laser that's entirely fiber coupled until it gets into the dark box. And then once it's in the dark box, it turns into a free beam where it passes through a notch filter over eventually to the sample, where we then collect the Raman scattered light. The Raman scattered light then passes through a long pass filter and is then recollected into a fiber, which then goes to a spectrograph and ultimately a CCD camera. And so my first proof of concept samples, just to kind of prove that this setup works and I can actually generate fluorescence removed Raman spectra. I just took a couple powder samples of alizarin crimson or PR83, Carmine Lake or NR4, and Lac dye. And I was able to extract fluorescence removed Raman spectra that have high fidelity to the spectra for these samples that are prepared, that have been demonstrated and documented in the literature. So each of these point spectra were collected over the course of a minute. And if I'm going to do hyperspectral imaging, a minute-long scan is not super feasible. So I reduced the scan time to just a one collection of a 5 seconds Raman spectrum. And while my signal to noise ratio has definitely decreased, I'm still able to isolate discernible and unique bands that I can ultimately use for fitting for generating hyperspectral images going forward. And so with this in mind, with a 5-second integration per pixel, one 32 by 32 pixel image can be collected in about 1.5 hours. So it's a much more reasonable experimental time than if I had stuck with the 1 minute long collection time per pixel. So keeping forward with proof of concepts, but then moving away from just the pure powder to then let's actually look at paint as applied to paper. So all of my paints that I prepared were 5% weight by weight, suspended in Kremer watercolor medium, which is a mixture of gum arabic, honey, and glycerin, and applied to just a standard piece of notebook paper. And so the macroscopic photo of what, so starting with alizarin crimson, which is a synthetic organic, but it happens to have quite a nice Raman scattering cross section. So the bands are quite easy to see above the baseline anyway. So we have our macroscopic photo. This is the microscope image that I took of where the hyperspectral imaging actually occurred. This is a 50 by 50 micron area. And so as you can see from a pixel that I've extracted from the data, I've gone through and fit at each pixel this band at 1486 wave numbers, which is characteristic of alizarin crimson. And as you can see from this image, where the more intense the pixel, the higher the presence of this particular band. And you can see that it correlates quite nicely with where the larger particles are present in this image. So going on then to Carmine Lake, again, prepared in the same manner. In this case, when we look at an extracted pixel, I should say that these are the raw spectra that I'm showing here, and I'm only doing 2 wavelength steps instead of 4, just as another experimental time constraint. And this really highlights the need for the SSE processing technique for then generating these hyperspectral images. Because if I were to, there are really no discernible bands at all that I can find in these raw spectra. But when I look at my SSE process spectrum, and I do these SSE processed spectra at each pixel, I run through a separate algorithm for peak identification, where it only pinpoints a peak if it is greater than 5 times the RMS noise of that same spectrum. So it is able to find this peak here at 1324 wave numbers, which is characteristic of Carmine, that I would not have been able to see otherwise because it's entirely swamped by this fluorescent background. And again, at each pixel, looking at that peak intensity at 1324 wave numbers, we can see that this also correlates quite nicely to where the pigment particles are most highly concentrated within the sample. And then lac dye as just a final point. The spectrum slightly changes with lac dye when it goes from being in its powder form to then being incorporated into a binder. And the same sort of visualization we can see. This is a slightly noisier image because it's a lower sampling density. And that's just because lac dye is significantly low Raman scattering. And so it really does benefit from having a higher integration time. So in order to keep the sampling time reasonable, I went to a lower sampling density, but a higher integration time to still keep the experiment at about 1.5 hours per image collection. But again, we can see this dark area corresponding to this area of no pigment, whereas these slightly more fuzzier areas corresponding to the high density of lac dye seen through here. I'm running a little low on time, so I apologize. I tend to talk a bit more than I always anticipate. But just really quickly, the next step was to see if I could discern side by side. So these paints were actually prepared in gloss acrylic medium and painted side by side. We have lac dye on top here, the alizarin crimson, the Carmine Lake, and then this is actually a small sample of Madder Lake, which I unfortunately don't have time to talk about today. The microscope image of the imaged area shows the alizarin crimson on top here and Carmine Lake on bottom, and we can clearly see the separation from the fitting of the 1488 wave number band corresponding to the PR83 versus the 1324 wave number band corresponding to the NR4 or Carmine Lake. Likewise, in this area right here, we have the alizarin crimson on top, lac dye on the bottom. Again, fitting of the 1488 wave number peak shows high fidelity to the PR83 regime, and then a fitting of the 655 wave number peak shows a high fidelity corresponding to the lac dye. So this technique can now show side-by-side comparison and isolation of 2 red lakes side by side. In the interest of time, I'm just going to talk about this one sample that I mixed them together in the same paint. So whether these pigments on the microscale can then be discerned. So this is a sample that I prepared of alizarin crimson with Carmine Lake in that same Kremer watercolor medium. the macro scale version of it right here, and then the imaged region right here. So if you were to just look at the imaged region, there's really not any visual difference that there is more than one type of red lake pigment in this region. However, when you go through and do the fitting of the band at 1488 wave numbers, which is unique and specific to alizarin crimson, gives us this resulting hyperspectral image here, where we can clearly see that this pigment particle here is alizarin crimson, as well as a lot of these other smaller particles, smaller particles throughout the microscope image. And then when we then go and fit the band at 1324 wave numbers, what we see is a slightly more complicated image. And that's because the band at 1324 wave numbers for Carmine Lake is actually quite close to a known band for alizarin crimson at 1333 wave numbers. And so the main difference between these two images you can see are in this particle right here. So then we can actually look at the data in a slightly different way. Instead of collecting these two peak intensity maps, which are what's shown right here, we can alternatively generate a peak location map. And so from this peak location map, we can see that anything in purple would correspond to a wave number location of 1324 wave numbers, or the Carmine Lake. And then anything in orange would correspond to something around 1333, or that band that is known to be present in alizarin crimson. And so as we can see, this particle here corresponds nicely to this region that's in purple here, which means that this particle, and most likely this surrounding region right in here, is actually Carmine Lake majority. I did also apply this technique to a mixture of alizarin crimson and lac dye. I'm running short of time, so I'm not going to talk about it in detail. But in conclusion, I have been able to successfully implement a sequentially shifted excitation Raman processing algorithm for the point spectral analysis, as well as hyperspectral imaging of red lake pigments that has been completely fluorescence corrected. And I have been able to show that this technique is successful in distinguishing between different red lake pigments on both a macroscopic and a microscopic scale. In the future, this technique would, I think, really readily lend itself to being made into a portable version. The control box for the laser is quite small. It's only about yay big. And spectrographs these days can be quite miniature. And so creating a fiber optic portable system, I think, could be quite interesting indeed. So just quick acknowledgements. I'd like to thank the Material Measurement Lab and NIST for hosting me for my fellowship, the National Academies of Science, Engineering, and Medicine for providing me my National Research Council fellowship, my advisors, and all of you all for listening to me go over a bit too much. So a quick bibliography in case you're curious. This is great for some sequentially shifted theory and those SSE applied to cultural heritage using that commercially available portable instrument is shown here. And I will happily take any questions that we might not have time for or may have time for, whichever.
Oh, no problem. That was fascinating, Kristen. Such an innovative method of identifying those elusive red lake pigments. I do have a question. Have you tried using this method on actual work yet?
No, not yet. Yeah, I just kind of got to the point where I was able to get it to discern between the mixed pigment samples, but yeah, definitely next step would be applying it to an actual object or historically an aged control sample, for example, just to see if I can still pick out unique identifying markers in the Raman signature for degraded red lakes, for example, or photo damaged red lakes.
Well, I am excited about the development of this new method, but also the fact that you just coined a new scientific term in Smarticles. So
yeah, Smarticles is quite great.
It's a good one. Well, thank you, everyone. I don't think we do have time, and I think everyone pretty much covered their questions in the chat. Please do look on our YouTube channel. This will be posted there. So if you missed anything or need some information, I think everyone put a lot of great information in their slides. You can certainly go back to those. And I want to thank everyone. I want to thank our we had some really incredible talks tonight. And thank you so much to our speakers. And thank you for tuning in, everyone that's here. Please join us again next week for our third ring, where we explore the great beyond. And have a great night. Good evening.
Good evening.